We're going to start with an easy example of calculating the distance between 2 points in 3 dimensions. And let's take the 2 points to be, let's say I want the distance between 2, 3, -4, that ordered triple, and 1, 3, -4. So I'm going to start with 2 ordered triples where 2 of the coordinates are exactly the same. And then in the next example, one of the coordinates will be the same. And in the last example, none of the coordinates will be the same. So you can see one of each type here. So the natural thing to do would be to plot both of these points in 3 dimensions, but I don't recommend that. Since I just want the distance between them, I'm going to plot one point, and then I'll measure to plot the other point. You'll see what I mean by that. For example, let me say that I plot this point first, 2, 3, -4. Let's just say it's right here in 3 dimensions. And then I need to know how to get from here. So this point is this guy. And I need to know how to get from here to this. Well, notice that the x over here is 1 less than this x. So what that means is and remember the x is the forward or backward dimension. So if x is 2 and I need to go to x equals 1, that means from the yellow point I need to go back 1 unit. Okay? And then the 3 is my y. The y is the left or right, so I need to go 0 left or right. And finally, the -4 is my z coordinate, which is up or down, and they're the same, so I have 0 up or down also. Okay? So from this point, I go back 1. And remember the x-axis is angled like this. So if I go back, I need to go back in this direction or forward in that direction. So from here, I go back 1 unit, and that's it. That's my other point. The distance between those 2 points is 1 unit, no problem. So the answer to this question, the distance between those points, is 1 unit. And notice I did not draw my x, y, and z axes because I didn't want this to get too crowded, too hard to understand. Okay, and that'll be more valuable as these calculations get more complex. So let's do another one. So now I want the distance between these 2 ordered triples, and you can see now the only coordinate they have in common is the z coordinate. So I do the same thing. I plotted my yellow point here just somewhere, and then I'll measure from that back, right, up, down, whatever to get this other point. So from this point to this point, my x decreases by 1, so I need to go back 1 unit, just like I did before. My y increased by 2. Y is left or right. If it increases, I need to go right 2 units. My z, no difference. So I go up or down 0. Okay, so here we go. From this point, I go back 1, and back is measured at an angle. So I go back 1, so I'll sort of draw a dashed line here, label that with the number 1. Then I go right 2, so I'll go right 2 units, label that 2. And then I go up 0. So what I get here is a rectangle. And now I need to locate where this point here is. So I have my rectangle, so I can go back and backtrack it. Again, I'm sorry if this one's really simple again. I'm trying to establish good habits for when you get to the examples where none of the coordinates are the same. So you didn't need the entire rectangle here to do this, but it's a good habit to get into. So I went back 1 and right 2. There's my other point. So this guy lives right here. How do I calculate the distance between those? Well, that's really simple because the distance I'm looking for is this guy right here, and I can use a right triangle because remember, these are all right angles. So the distance here would be the Pythagorean theorem. The back distance is 1, the horizontal distance is 2, so I have the square root of 1 squared plus 2 squared, which equals the square root of 5. So these 2 points, the distance between them is the square root of 5. So we still haven't really run into anything where we have to use the three-dimensional distance, and that's what's going to happen next when none of the coordinates are equal. So if I start with this point now, and I need to go to this point, I'm going to write all my measurements. So my x goes from 2 to -6. That means I need to go back 8 units. And then my y goes from 3 to 8. That means I need to go to the right by 5 units. Finally, my z goes from -4 to 0. That means I need to go up 4 units. So I need to go back, right, and up. So maybe let's put our point down here so we have space to go back, right, and up, and see if we can figure out how to get to this guy and how to measure the distance. So I need to go back 8 units. So I'll just, let's use a dashed line again. So that's 8 units. I need to go right 5 units. So I'm just labeling this as 5. I need to go up 4 units. And now, from all of this, I'm going to draw a box. And lots of ways to do this. The easiest thing maybe to do would define your rectangle, which would be, this would be a simple rectangle to draw. And then I go up to this point, and I need to go right 5 units also, and up 4 units, just like I did back here, and get another rectangle. And then connect the corners, the vertices of my rectangles. And now I have a box. So I have a starting point. I need to figure out where this point is on my box. So let's go back and track this from my starting point. So I go back 8, right 5, up 4. So the point that I have now is this guy. And I need to know the distance between the yellow point and the blue point, which means I need the diagonal distance across my box from corner to corner. Sorry, that didn't draw as red like I wanted. Let me see if I can get that. Okay. So I need to know this three-dimensional distance. And so what you could do is, since I'm joining this corner to this corner, try to make a right triangle out of that. And you can do that. Clearly, this would be a side of the right triangle. And now I need to connect this point down here to this point down here. And that, in fact, is a right triangle, because the floor of this box is perpendicular to the walls. So in this right triangle that I have, let me redraw it over here roughly. This is the right angle. I know this is 4. I don't know this, and this is the thing that I really want. This is the distance that I really want, right? The hypotenuse of this right triangle. So what I'd like to do now is figure this out. I can do that, which is the same thing as this distance down here. I can use that as part of a different right triangle on my floor. Right? This would be a side, and this would be a side here, and here's my right angle. So if I look at that right triangle, roughly again, this distance here is 5. My back distance is 8, so this is 5 and 8. So this would be the square root of 25 plus 64, which is the square root of 89. So I could bring that back up here and say this is the square root of 89. Now, in this right triangle, Pythagorean theorem, this distance would be the square root of 89 plus 16, which is 105. So there is the distance between those 2 points. And that's how you calculate the distance between points in 3 dimensions. It's 2 applications of the Pythagorean theorem. And that only happens if when you plot your 2 points, you get a box between them. If none of the coordinates are the same, you're going to get a box. If one of the coordinates is the same, you're going to get a rectangle. If 2 of the coordinates is the same, you're just going to get a line between them, like we did in that first example. So there you've seen all 3 cases. I hope it makes sense. I think this last case is pretty interesting, kind of fun, and I hope you enjoy it.